Hello, my name is Adam Hausneck. This set of slides helps to provide the mathematical and programming background necessary to complete the Tangent Approximation Python app. This app can be used as an aid for visualizing the numerical approximation of the derivative. The goals of this module are: first, to learn how to numerically approximate the derivative of a function at a point. Next, to complete a Python app that uses secants to visually approximate the tangent line at a point on the graph of a function. And here we have a snap of the running application, and you will notice that there's a left secant here, and also we have an accurate tangent line. I'll say more about this app later. To complete the app, you'll need to learn about the practice using the Python mathematical packages matplotlib, numpy, and scipy. These are widely used packages. You also need to learn how to create a Python package or library which can be imported by other programs. This is done so that you can reuse programs that you write or functions that you write in other programs, or you could give your library to somebody else so that they could use code that you've written with their programs. So now we're going to go over a brief mathematical background needed for this app. You actually may need to consult a calculus text for more details. First, we need to go over the formal definition of a derivative. Recall that you need an open interval. That's what this represents here. It's all the points between A and B, but A and B are not themselves included. You need a real-valued function defined on this interval, and you need a point x0 within the interval. Given this information, you can define the derivative at x0 by this limit. Inside the limit, we have what's called a difference quotient. You have f of x0 plus h minus f of x0 divided by h. Of course, for this definition to be valid, the limit has to exist. The other point I want to make is that when h goes to 0, that means that h can be any small value, positive or negative. It just can't be 0, because then you'd have division by 0. Now here's a figure with all the quantities labeled. And you can see in this case, the numerator represents this drop. That is, f of x0 is actually above f of x0 plus h. So the numerator is actually negative, while the denominator is actually positive because x0 is to the left of x0 plus h, or x0 plus h is actually to the right of x0. Now, you may already know this, but this can be expressed in terms of 2 points, x1 and x0. If you just let x1 be x0 plus h, then h is nothing more than the difference between x1 and x0, and f of x0 plus h can be written as f of x1. So then you can express this limit as f of x1 minus f of x0 over x1 minus x0. And here, x1 has to become, the idea is x1 has to become arbitrarily close to x0, but it can't equal x0, otherwise, again, you'd have division by 0. Now, this is actually, by many, a preferred definition for the limit, for the derivative, because the numerator can be thought of as y1 minus y0. That is, you can think of f of x1 as being y1, f of x0 as being y0. And so this looks like y1 minus y0 over x1 minus x0. So that resembles the way you define the slope of a line. So here is the figure above now translated in terms of x1 and x0. Okay, now one thing you have to be careful about is h need not always be positive. So h can be positive or negative. The only value it can't be is 0. So here's an example where both h is negative and that is, the denominator is negative and the numerator is negative. The numerator is, again, negative because f of x0 is above f of x0 plus h, and the denominator is negative because x0 plus h is to the left of x0. So this is a left secant, and it has positive slope, and that makes sense because both the numerator and denominator here are both negative, so the ratio is positive. And just to remind you of that, I've expressed it this way. The slope in this situation, the slope of the secant is positive. Now, you can also express this in terms of x1 and x0 if you wish. So here's the corresponding figure. And again, of course, this ratio is turning out to be positive in this situation. Thus, we see if h is small, negative, or positive, then on the one hand, this difference quotient represents the slope of the secant, and on the other hand, if h is small enough, it's also a good approximation for the derivative at x0. Thus, we can use the left and right secants to approximate the tangent line at x0, f of x0, and their slopes can be used to approximate the derivative at x0. So here I have a diagram that shows a left secant, a right secant at 1.5, 3.88 of this built-in quadratic. And here's also an accurate representation of the tangent line. Now the left secant has a slope of minus 1.25, and the right secant has a slope of minus 1.64. And neither of these are as good of approximation as their averages to the slope of the true tangent, which is this black dashed line. In fact, the slope of the true tangent is minus 1.5, and you can see that by just actually differentiating the quadratic and substituting in 1.5. So here I'm showing you the arithmetic that I used to calculate the average, and we can see that the average is actually much better approximation than either the left slope or the right slope. So this idea is to use an average to come up with a better approximation for the derivative is what we're going to explore in this slide. What we're going to do is assume that h is greater than 0 and that HL is going to be minus h and HR is h. That is, here we have the slope of a left secant, and here we have a slope of a right secant. But we're assuming that the HL and HR have the same magnitude. So if we make the substitutions for HL and HR, we get this expression for the average. And now we can see that we can factor out the h out of the denominator. And so we wind up with this expression. Also notice that the right terms, they remain as they are, but the two numerator left terms actually switch signs because the denominator is negative. So this causes cancellation to take place between f of x0 and minus f of x0, and we have this simplified formula which represents a good approximation to the derivative. And the idea is that this approximation is better than either the left slope or the right slope would be. So here I have a diagram illustrating the algebra. But you can see here is we have XL, which is X0 plus HL, which is a minus H, so it's really X0 minus H, and XR is really X0 plus H. So we have this pink point and this blue point here, which are the 2 points on this quadratic, and we have a secant line passing through them. And that the slope of that secant line is just given by this formula right here. So in fact, this secant line is called the central secant line, and this approximation is known as the central difference approximation, or the 3 endpoint derivative approximation for df dx at x0. And notice that the reason why this is called the 3 endpoint derivative approximation is because we start off using 3 points. Namely, we start off using x0 plus hl and x0 plus hr. So we had 3 points in the beginning, but after the algebra simplification, we wind up with just 2 points being involved. Now, the other thing you should notice, something surprising, that this central secant is actually parallel to the true tangent. And you might be surprised by this, but it turns out that it's exact for quadratics. That is, the central secant always gives you the exact result for quadratic functions, and actually for linear functions. It's not very difficult to prove. You might want to try proving it. Okay, next I'm going to talk about the graphical user interface for the tangent approximation app. It's also known as a GUI. Okay, here you have a screen snap of the app. And now to get started, you either need to click in this edit field and enter a value for x0, or you can move the cursor around over the graph area and click to enter a value of x0. In either case, the value of y0 will be computed by the app using the formula for the function. Now, once you have a secant entered, you can improve the approximation by clicking this forward arrow button. Or if you want to go back to a previous approximation, you can click the previous or back arrow button. And if you've done a number of approximations in a row, that is, used a number of secants in a row to approximate the tangent, you can restart the sequence by clicking this reset button. Now, you can choose the method you want to use by clicking one of these radio buttons. The first uses a single left secant. The second uses a single right secant to approximate the tangent. This third uses both a left and right secant to approximate the true tangent. And the central uses a central secant to approximate the tangent. If you click in this checkbox down here, you'll plot the tangent line. That is, an accurate representation of the tangent line will be drawn, and the slope of the tangent line, which is the same as the derivative of x at the value of x0, is shown. If you want to restore the app to its initial configuration, or clean out everything except for the choice of the method, you can just click this button. And finally, you can click on the quit button to quit the app. You can also click the little red button at the top on a Mac, and I believe on Windows and Linux, at least some versions of Linux, you can click a little Xbox on the right top to quit. Okay, now I'm going to talk about completing the tangent approximation app. To complete the project, you'll need to learn the following. First, how to use Python functions, including lambda functions. You'll also need to learn how to use Python lists and tuples. You'll need to learn how to create NumPy arrays from lists and also by using NumPy's linspace function. You'll need to learn how to evaluate mathematical expressions using NumPy arrays and NumPy's mathematical function library, which includes special versions of all the standard mathematical functions, including absolute value trig and other functions. Now, the reason why you want to do this is because this gives you a way of avoiding the need to write loops to evaluate, to generate values necessary for plotting and also for doing other kinds of computations. You also need to learn how to use Matplob's axis object to plot a function and how to use it to label the function. Finally, you'll need to learn how to use Python's try except statement to write test functions to use with the app other than the built-in quadratic. So here is a list of references and links and so forth for documentation and other kinds of references. So first, here's a link to where we obtained the Anaconda Python 3 distribution. That's a distribution we used to write the app. We use this distribution because it includes the packages matplotlib, numpy, and scipy, so you don't have to install them yourself. Now, here's a link to scipy.org. This will have a whole lot of links to other documentation, including documentation for matplotlib, numpy, and scipy. Beyond scipy.org, there are numerous sites that have examples, videos, and documentation for matplotlib, numpy, and scipy. In fact, if you have a bug in your program, if you search internet, you can probably find sites which will explain what the bug is and how to fix it. So now the Anaconda Python distribution also includes SpiderID, which is a special editor for writing Python programs. And now you can obtain documentation about it and actually download it if you want from this www.spiderid-ide.org. There are actually tutorial videos for Spider and other kinds of documentation. Now, to complete the app, you'll need to actually write the following functions or complete the following functions in the tangent approximation student lib.py. First function you'll need to complete is a secant line function, the next h function, the generate left or right secant slope and points function, the generate central secant slope and points function, and the plot the function. Now, I just want to point out that functions 3 and 4 don't actually plot the secant, rather they are actually calculate or generate the values necessary to plot the secant. And that's what both of these do. On the other hand, plot the function actually plots the test function func over the domain from xmin to xmax and uses the label string to label the plot of the function. Okay, here are some details. So here's what you would see in the student version of the library. That is to say, you're going to see what you might call a skeleton of the functions that you need to complete. So for example, for the secant line, this is the skeleton. You're given x, m, x0, and y0, and given these quantities, for the value of x, you're supposed to compute the corresponding value of y for the secant line passing through x0, y0, which is the point at which you're trying to find the derivative or the tangent line. And you're also, this secant line has slope m. So really all you're doing is given the value of x, computing the corresponding value of y. So the next h function, given the preceding value of h, which is passed in, you're supposed to calculate the next value of h. And now a commonly used way to do this is to take 60% of the current value. You could use a larger or smaller value. If you use too large a value, then the convergence of the secant lines to the tangent will be very slow. If you use too small a value, then the convergence will be so quick, or will happen so quickly, that you won't be able to notice any particular way that the convergence occurs, or anything special about the convergence. Okay, so in any case, what you have to do here is return the next value of h. So now the generate left or right secant slope and points function. Here you're given the test function as input, x0 and y0, which is the point at which you're trying to find the true tangent, or approximate the true tangent. And you're passed in the value of h, and you're also passed in the domain of the test function. Given this information, you need to compute x1 and y1, that's the other point on the secant line, and you also need to calculate the slope of the secant line through x0, y0, and x1, y1. And now using the function, the test function m, x0, y0, you also need to compute the x values and y values necessary to plot the secant. However, this function doesn't actually plot it. All it does is generate the values necessary to plot the secant. And these values, x values and y values, are actually arrays. So you'll need to return all this information as a tuple, and the order in which you do this is m, which is the slope of the secant, x1 and y1, which is the other point on the secant, and the x values and y values, which are the generated values needed to plot the secant. So here is the rest of the functions, or the skeletons of the rest of the functions you need to complete. First is the generate central secant slope and points. Again, you're passed in the test function, x0 and h, and you're also passed in the domain of the test function. Given this information, you need to compute the left point of the central secant, xl, yl. You also need to compute the right point, which is xr, yr, that lies on the central secant. You also need to compute the slope of the secant through those 2 points, that is through xl, yl, and xr, yr. Finally, given this information, that is the xl, yl, xr, yr, and the domain, and the slope m, you need to generate the x values and y values necessary to plot the central secant. And now these are actually arrays of values. What you actually return then is the slope of the central secant, followed by xl and yl, that is the left point on the central secant, and xr, yr, the right point on the central secant, and x values and y values necessary to plot the secant. Again, this function does not plot the secant, it just generates the values necessary to plot the secant. Finally, the last function you need to complete is this plot the function. Here you actually do want to graph or plot something. You're going to use a matplotlib axis object to do that. Here's the test function, and here's the domain, that is xmax is the domain of the test function, and you also have a label string. So you're supposed to plot the function over the domain, xmin to xmax, and you want to do this using 300 x values and y values. Now, and you also want to use the label string to label the plot. This function does need to return something. It actually returns the minimum value and the maximum value of the calculated y values. So it's actually the y min followed by the y max. That's what this function should return. Okay, now I'm going to describe how you run the completed app from Spider. Now here I have example 0 file inside Spider, and I'll say more about example 0 later. But I just wanted to show you what the Spider interface looks like. And this is version 5.05 of Spider. Okay, now it turns out that there's a bug in the normal way Spider executes programs, so you have to change that. To do that, you need to click on the wrench icon at the top of Spider's window. This will open a preferences window. Here it is, and you also need to click on this run item in the first column. This will display the following pane. And now within this pane, you need to make sure that this execute in an external system terminal is selected. This way, Spider will run the application program in a separate terminal. And this needs to be done because the tangent approximation app generates its own window and graphics, and that causes a problem for Spider if it's run inside of Spider. So once you've done this, you can click Apply and OK. Okay, to run this, you have to have both the approximation app version 1.py and the tangent approximating student lib, that is the completed version, in the same directory. And so you need to create the example 0.py file. So here it is. Now this is just a very short program so that you can run the app from within Spider easily. So all you do is import in the tangent approximation app version 1 as app. Here I'm just using a print statement so that when the app, this little piece of code is run, you recognize the fact that it's running. And here I'm just indicating that we're going to, by default, it uses this quadratic as the test function. Finally, to cause the app to actually launch, what you need to do is say app.tangent approximation with a left and right parentheses with nothing in between. Actually, this is a class, and this is just creating an object of that class. Now, finally, to actually, once you've written this example 0 file, to actually run it, you just click the green Run button. Now what Spider does is opens a terminal automatically and runs a small script which launches the app. You should see the output from the print statement, namely example 0 default function y is equal to 10 minus x squared over 2 in the terminal window. And the function, that is the application should launch. And so here's a snap of the launched application. I'm just reminding you how you quit the app here. So when you quit the app, you should see the following message: tangent approximation app ending, bye-bye. Now you can actually run example 0 directly from the terminal window if you want to, rather than using Spider. Again, you have to have the tangent approximation app v1.py and example 0.py in the same directory as along with your completed library. So here I'm showing you how to change directories to the tangent approximation test directory, which contains these files. And here I'm using a terminal window to do that. And now after you've switched to the proper directory, here I'm showing you a listing of the directory by using the ls command. And you can now run the example 0.py file by just entering Python example 0.py and pressing the return key. Of course, as before, the default function will be used. And again, I'm showing you a snap of the running app and again how you quit. Now finally, you can also run the app just directly from the terminal without using the example 0.py file by entering the command python tangent app v1.py. Of course, both the application and the completed library have to be in the same directory to do that. So here you can see the student approximation live.py, which is presumably is completed, and the actual program, that is the application program right there. And you just type Python, the name of the application program.py, and just press the return key. So now I'm going to show you a series of examples of how to use your own test functions with the app. To do that, you're going to have to learn how to write Python functions that include the use of both lambda functions and also the try except statement. So here is an example. I want to use 2x sine x as my test function, and so now I have to import the application, the actual app, as app, tangent approximation app version 1 as app, and I also have to import numpy. Now here I'm just using a print statement, so I know that this piece of code is actually running correctly in case for some reason the app itself doesn't launch. And now down here, you can see I've created two lambda functions, one representing the function itself and one representing the derivative. Now inside I'm using a numpy, and you have to use numpy here, otherwise the app won't work. That's why I had to import numpy as np. So I'm using the sine built into numpy and the cosine built into numpy. So here you can see that how I've called the tangent approximation class function class. This actually is creating an object of that class. And to call it, I have to pass in my two functions and a domain that's minus pi to pi, and also some string to represent the way you want the plot labeled. Here I'm passing in some LaTeX. Here's the result of running this short application. You can see the functions plotted and it's labeled, and you could go and use all the tools as I've shown in another demo. Here's a second example. This time I'm trying to use, or I'm using the absolute value of x as the test function. Again, I'm importing the app and also NumPy. And also I'm printing a statement so I know what this piece of code is doing. Now this is a little bit different, and I have to use a NumPy because here in the definition of the function I'm using NumPy's version of the absolute value in order to have a correctly functioning app. And also the other a little bit different thing I'm doing is I'm passing none for the derivative. In this case, because I'm passing none, SciPy's numerical derivative method will be used to calculate the derivative of the function. And this is what how you actually call tangent approximation. F df dx, and here's the domain, and here's a little bit of LaTeX to label the plot. And this is what you get when you run the app. Or this, I'm sorry, not the app, this little piece of code. Okay, here's example 3. Now here's, I included this example because this function will cause a division by 0 error at 0. And so when I define the function, I have to use a try except instead of using a lambda function. Again, I'm passing in none for df dx, so SciPy will actually be used to calculate the derivative, and this is how you call the function. This time I'm only plotting it from -1 to 1, and here's a little bit of LaTeX I used to label the plot. So this is the graph you get. You can see that this particular function is fairly complicated at the origin. Now here's a fourth example. I'm giving this example because it turns out that when you have a fractional exponent, you have a problem at when x is actually a negative number. So down here I have to use a little bit of a trick in order to get away with using a lambda function. Now I guess for this app, I did have to bring a NumPy, I forgot, because I'm going to use it down here for the derivative. But up here, the trick I'm using is I'm actually squaring the function and then taking its third root. The reason why I need to do that is because if you take, if we were to take a cube root of negative numbers, that is, a negative number to a fractional exponent, you can wind up with a complex number as a result. So to avoid that is to say our app only can work with real numbers, to avoid that problem, I'm squaring x first. That makes it positive, so it's safe to take its cube root. Now down here, I'm doing the same thing. I'm squaring it first and then taking its sixth root. But then there's another problem with this one, and that is when I square it, I lose information about the sign. So I have to correct for that by using np sin x here in order to obtain the right result for the derivative. And I have to put the whole thing in a try except block because this function can cause division by 0. And finally, this is the way I call the tangent approximation object, or create a tangent approximation object, and by f df dx minus 3 to 3. And this is a little bit of LaTeX necessary to label the plot. Okay, and this is the plot you get, and to me it looks like whiskers or maybe insect antennas. In any case, some people think of this as being very similar to the absolute value plot. However, these two whiskers, so to speak, are actually curved. Also, there's a real problem at the origin, which you can discover if you explore a little bit. In any case, the slopes along these lines are not constants. Okay, here's a fifth example. This time I wanted to plot 1 over x, and now originally I was thinking of plotting it from minus 10 to 10, but it turns out that doesn't give a good plot. Maybe you can find a way to get a decent plot. In the end, what I decided to do is to plot it from 0.1 to 10, which is only through positive values. So actually, I really didn't need to use this try except plot, but if you want to plot across an interval containing 0, you will need it. And here only reason I imported NumPy was because of this return statement right here. Now notice the function itself, I just used a lambda function to do that. However, normally this would cause an error, so probably I should have used a try except block here, except that I realized I was going to restrict myself to plotting only positive values or only negative values. In this case, I plotted only positive values, so I just left it as a lambda function. And so this is what the plot looks like. Okay, so here's example 6. I decided to give this example as one more example where I'm using lambda functions. This I've commented out NumPy because for this example you don't need NumPy anywhere because these are just rational expressions. And here all the rest is straightforward. I'm just plotting it from -2 to 2, and this is a little bit of LaTeX I used to label the plot. And so this is the plot I get. You can see it's a relatively well-behaved plot. Okay, that's it. Thanks very much for your attention. Good luck with completing the app.